Hello everyone, my name is Marcel, and I will be presenting our work on generating subpopulation-specific biventricular anatomy models using conditional point cloud variational autoencoders. The human heart exhibits considerable inter-person variability in terms of both its anatomy and function. This characteristic has a significant impact on cardiac disease prevention, diagnosis, and treatment in clinical practice. Therefore, it is crucial for any computer-based model of the heart to be able to accurately capture this variability. Such a model has a variety of benefits and possible use cases, such as clinical outcome prediction, population-specific shape analysis, dimensionality reduction, or computer modeling of cardiac mechanics and electrophysiology. Accordingly, the objective of this work is to develop a deep learning model capable of generating virtual subpopulations of three-dimensional biventricular anatomies. This is a challenging task for multiple reasons. First, every generated cardiac anatomy representation needs to have a realistic appearance in terms of both its size and shape. Second, the synthesized population of anatomies needs to have similar levels of diversity as the true population and avoid collapsing to a mean shape. Third, differences between various subpopulation-specific characteristics, such as sex, should be accurately represented in the morphology of the generated hearts. Fourth, the generation process should be as interpretable as possible in order to improve understanding of the model and facilitate clinical acceptance. Finally, fast per-case generation times would be desirable to allow efficient scaling of the process to larger population cohorts. In this work, we propose a novel, conditional, point cloud variational autoencoder capable of generating subpopulation-specific biventricular anatomies. It consists of an encoder-decoder architecture that is embedded in the well-established variational autoencoder framework. The network works directly with point cloud representations of the multi-class biventricular anatomy, which enables the usage of high-resolution data. The encoder is an extended version of the PointNet++ architecture, while the decoder expands the point completion network to our multi-class high-dimensional setting. The network outputs both a coarse, low-density point cloud to represent the biventricular anatomy on a global scale, and a dense output point cloud to capture the anatomy on both a local and global scale. Conditional inputs such as sex and cardiac phase are introduced into both the encoder and decoder part of the network to enable subpopulation-specific processing. Following the framework of the beta variational autoencoder, the total loss function of our network consists of both a reconstruction term and the standard Kullback-Leibler divergence term with a weighting parameter beta. We use this parameter to control the trade-off between the reconstruction and latent space quality and fine-tune it specifically for our dataset. The reconstruction loss consists of two terms, a coarse loss term and a dense loss term, weighted by a parameter alpha. For the coarse loss term, the low-density output of the network is compared to the gold standard point cloud, while the difference between the high-density network output and the gold standard point cloud is used to determine the dense loss. The chamfer distance between the reconstructed and gold standard point clouds provides an approximate surface-to-surface distance between the anatomies of each biventricular substructure and is used as the loss function for both terms in the reconstruction loss. We set the weighting parameter alpha and the loss function to small values at the beginning of training in order to force the network to initially focus on a good coarse reconstruction. We then gradually increase its value to put more emphasis on the dense reconstructions during later training stages. We use a dataset of 1,000 randomly selected cases of the UK Biobank study and split it into train and test datasets for method development and evaluation respectively. In our first experiment, we want to assess the reconstruction ability of our point cloud VAE. To this end, we pass the point clouds of the test dataset through a trained VAE and compare the reconstructed output point clouds with the corresponding input point clouds. We observe a good visual alignment between the respective shapes on both the local and global level. In order to quantify the reconstruction quality of our method's outputs, we calculate the chamfer distances between the reconstructed and input point clouds. We find values that are below the voxel resolution of the underlying image acquisition for all input conditions and cardiac substructures, which demonstrates our network's very good reconstruction performance. In our second experiment, we want to assess the ability of our method to generate subpopulation-specific biventricular anatomy cohorts. We choose two binary metadata variables, sex and cardiac phase, to model 4 different subpopulations. We then randomly sample latent space vectors of our VAE, concatenate the respective input conditions, and pass the results through the trained decoder to synthesize the biventricular anatomy point clouds. When examining the generated point clouds visually, we observe realistic shapes for individual point clouds and accurate levels of diversity across the population. The effects of different conditional inputs on the synthesized hearts are easily visible and plausible. For example, male hearts and hearts at end diastole are typically larger in size than female hearts and hearts at end systole. In order to evaluate the quality of the synthesized hearts from a clinical perspective, we convert both the generated point clouds and the gold standard point clouds from the test data set to meshes using the ball pivoting algorithm and calculate commonly used clinical metrics. We find comparable values between generated and gold standard anatomies for all clinical metrics and across all subpopulations. The metrics for female hearts and hearts at end diastole show a closer alignment with the gold standard than male hearts and hearts at end systole. In order to gain a better understanding of the generation process of the VAE, we analyze the contributions of different parts of the latent space to the generated point clouds. To this end, we vary individual latent space components while keeping the remaining latent space constant and pass the resulting vectors through the trained decoder to obtain the respective output point clouds. In the resulting point clouds, we observe gradual and interpretable changes to the biventricular anatomy without loss of a realistic appearance. We also find that individual components of the latent space encode different anatomical aspects, such as heart size, basal plane orientation, and midventricular diameter. All in all, our proposed method has several advantages. It can generate arbitrarily sized populations of realistic heart shapes while maintaining accurate levels of diversity across the population. It is robust against outliers and artifacts, and highly efficient at processing surface data due to its usage of point cloud representations. Our method is fully automatic, fast, and easily scalable, and does not require any point correspondence, registration, or landmark detection for training. It can model complex nonlinear relationships while maintaining good interpretability with a compact latent space. Furthermore, it is capable of taking into account subpopulation-specific differences and can process multiple cardiac substructures with a single network. However, our method also has some disadvantages. There is no point correspondence between the generated point clouds, and our validation was limited to healthy volunteers. We also did not explicitly enforce any temporal correspondence between individual generated point clouds at end systole and at end diastole. In summary, we have developed an easy and efficient geometric deep learning method capable of generating arbitrarily sized subpopulations of realistic biventricular anatomies while maintaining an interpretable latent space. Thank you very much for your attention.